So I believe we did that shifted triangle wave on Friday. And can somebody just remind me what we came up with? It was A sub n equals. After we did the shift. 1 over pi n. E to the j. 1.5. Wait, 1.5 plus n over 3? Or 1/2? Plus n over 3 pi. Where does the pi go? Outside this? So just like that? Okay. Okay, no problem. So practice writing MATLAB script. So here we go. So I've opened up myself a little editor. First thing I want to do is clear. That clears the memory. Next thing I need is a time vector. So what was the period of the signal? Was it 2 pi seconds? It's about 6 seconds. So if I want to look at maybe like 4 or 5 periods of this thing, I'm going to need maybe like 30 seconds worth. Does that sound reasonable? Should I go 0 to 30 or minus 15 to 15, or what do you want? I think we should go minus 15 to 15 so that it's easier to see the phase shift relative to 0. That's what I was thinking. But whatever. You can do whatever floats your boat. There's no right or wrong to this. Okay, so I need a time vector. So there are 2 basic ways to make time vectors. For right now, we're going to focus on the linspace command. And so basically, the way you set it up is I want to make a time vector that starts at t equals negative 15, ends at t equals positive 15, and then you can tell it how many points you want to put in the vector. I think it has a default of 1,000 maybe, but yeah, whatever the default is kind of wimpy. I'm gonna go for broke. Let's put 100,000 points in there, right? Why not? Just to make the point that MATLAB, like 100,000 points is not a lot of points. I mean, you've got this box on your desk. It's got 4 gigs of RAM, and you use it for all sorts of nonsense. Like 100,000 numbers is like chump change to your computer. That's the point I'm trying to make. Okay, and now we need to create the signal X. So the first thing I'm going to do is I'm going to define. I need to make an array X. That's going to be my signal, and I want X to have the same dimensions as T. So what I'm going to do is I'm going to start by initializing that array to all zeros. Has anybody programmed in C? Okay. When you program in C, you have to declare your variables, right? In MATLAB, you don't have to declare your variables. It's a big difference. However, it's still useful to declare your variables in MATLAB because there are certain benefits associated with speed. So if you declare your variables, it will run faster and kind of be a little less, I don't want to say unpredictable. It's a little smoother if you declare your variables, especially big arrays. So the way I'm going to declare it, what's the default, by the way, what's the default data type in MATLAB? Remember, in C, it's very well typed. So every variable you have to declare, this is a float, this is an integer, this is a whatever. So what's stuff in MATLAB? Doubles. Everything in MATLAB is a double. Yeah? Yeah, everything in MATLAB is a double, unless you specifically tell it that it's something else. What's that? Yeah, I mean, that's just the default. I had to pick something for the default. Otherwise, if there's no default, then you have to tell it every variable what you want. So a double precision is like the most precision. I mean, there is a quad precision, but I don't think it's really commonly used in sort of daily computing. So how does the float work?
I don't know how a computer recognizes the decimal.
It's actually really interesting. You guys want to do that for like 2 seconds? I can explain to you just kind of what goes on in the guts of the computer. It's let me pull this up real quick. Do we have internet? So, basically the way it works is seriously, Temple, could your internet be any slower? There we are. Okay, so let me see if there's a somewhere there's a cool diagram. Let's see. Let me just have a quick look here. So basically, okay, the way it basically works is this. Yeah, there we go. That's pretty good. So you can think of a floating point number like this. So, well, first maybe we should start with fixed point. So there's another decimal form called fixed point. And in fixed point, it's pretty easy. Like, you say your number has a certain number of bits. Okay? So, I don't know, 1, 2, 3, 4, 5, 6, 7, 8. Let's just stick with 8. It's a little bit more common sense. So in fixed point, you basically assume that the decimal place is always there. Okay? So then if you were to write like 10101101, let's see, the number before the decimal that's worth, do you know how to count in binary? Yeah, so it's 1, 2, 4, 8. So this number would be 8 times 1 plus 2 times 1. So this is 10 point. And then you count the fractions. So if every time I go in this direction I multiply by 2, if I go to the right, every time I divide by 2. So this is worth a half, a quarter, an eighth, and a 16th. So whatever the fraction is that's a half plus a quarter, that's let's see, that's 0.75, and then you add a 16th to that, which is like 0.0625. Okay, so whatever that works out to, 0.8125, if I did that right. Okay, so that's fixed point. And no matter what you do, you're stuck with that decimal point in the fourth dot. So there are pros and cons to using fixed point. The downside of using fixed point is that you're kind of limited with what range of values you can have. Like, you only ever have 4 points of precision. Okay? So in floating point, why did I erase that? In floating point, it's sort of a similar concept, except that the decimal could be anywhere. All right? So what you have is you have a sign bit. There's a really cool diagram I want to find for you. It's always one of those things that if I'm not looking for it, let's see. Come on. It's really embarrassing how slow the internet is in this room. Okay, so basically what you do is you have like 8 bits for the exponent, and then you have however many bits, like I think it's 27 bits, no, 23 bits for the actual fraction. So what's nice about this is your exponent could be, there we go. Let's try something like this. So your exponent could be like a really, really small number. So for example, if your exponent was like, so it's always like 2 to the exponent. So let's say if you have 8 bits, the smallest exponent you could have would be negative 127. So you could have 2 to the negative 127 times, and then like whatever the fraction that's here. So the way you work the fraction, it's like you do 1 point, and then in the same way that we calculated the fraction before, you do it the same thing here. So a half, a quarter, an eighth, 16th, and so on. So you have your fraction, and then you scale that fraction according to the exponent. So what's nice about the exponent is that, like, let's say your fraction was, let's say your fraction was just 1, 1, followed by all zeros. So the 1 is worth a half, the other 1 is worth a quarter, right? So you put those together, that's worth 3/4. So my fraction now is 1 point, the 1 is, there's always a 1 there. I don't know why, they always assume there's a 1. Okay. But now let's see what we're going to do with the exponent. So if you're, let's say your exponent is 0. So that means you're going to multiply by 2 to the 0. 2 to the 0 is 1, so that gives you 1.75. Okay, that's reasonable. But now your exponent could be, let's say, -1. What's 2 to the -1? 1 over 2. It's a half. Okay, so then you would have that number. Okay, your exponent could be -2. That would give you a quarter, so that would give you a quarter of that number. So you could go all the way down to -127. So guess how many zeros that's going to give you now? A ton. Okay, really a ton. So the advantage is with floating point is that if you need it, like you've got this fixed number of bits, like it's 32 bits for a single precision float and 64 bits for a double precision float. So if you're ever in a situation where you need like essentially 64 bits, 64, like a decimal followed by 64 zeros, you can have that. Okay? By the same token, you can go the other direction, right? What if I don't care about decimals? What if I want to save like a really, really big number? Right? I could make this positive 127. Then I would take my 1.75 and multiply it by whatever 2 to the 127 is. In that case, there would be barely any fraction associated with the number, but who cares? Like if I've got 100 billion, I don't really care if it's 100 billion.001 or 100 billion.002. Like basically, you'd lose your fraction. So the advantage is that with floating point, your decimal literally can float. So you have the advantage of you can either have really, really small numbers with a whole lot of precision, or you can have really, really big numbers where you don't care about like the precision of the decimal value. You just have a lot of range that you can stuff into like a small number of bits. The downside is it becomes really complicated to add and multiply these things, because when you have fixed point, it's easy. You're just adding bits like the same way you would add any old number together. But with floating point, like if you're going to add together two floating point numbers and they have different exponents, like how do you add together 2 to the 0 times 1.75 plus 2 to the 15th times 1.025, for example? Okay, now you've got this total headache where you've got to deal with you can't just like add the fractions, for example. Like now you've got to contend with the fact that the exponents are different. So you can squeeze a lot more range of numbers in, but it comes at the cost of having, the actual computations become more sophisticated.
Assuming that's going to lower performance.
Yeah, I mean, on the one hand, yes, but on the flip side, like this calculation, most processors now, and by now I mean like for the last 20 years, have like dedicated hardware to just do this stuff. Because that's really at the core of your computer, right? I mean, anything that you do, whether it's graphics, whether it's number crunching, whether it's surfing the web, I mean, at the end of the day, there's just a lot of number manipulation. So basically, like at the factory, when they're designing the instruction set for the chip, they basically have engineers optimize the circuitry and the instructions for doing these kinds of numbers. So it's at the point now where like your computer can probably multiply two floats on a single clock cycle. So it's really like no worse than any other computation. But it means that somebody had to sweat it at the factory. But for the end user, it doesn't really make a difference. But it is more like it does consume more power. Where it does make a difference is like in my lab, we do some work where we do some custom hardware. Like what we'll do, for example, field programmable gate arrays, which are like it's programmable hardware. And there, like, it really makes a difference, because then you have to kind of decide, well, do I need fixed point? Or like, can I use fixed point, or do I really need the computational expense of doing doubles or floats, for example? Because if I do that, then let's say I'm using a battery-powered part, it may require more power to do those calculations, or it may take like more transistors on the chip to do those calculations. So in some of those specialized applications, it could make a big difference, because you actually have to worry about it. But for something like a cell phone or a laptop or whatever, it's like a non-issue. Do you have a question, Justin? Oh, okay. Just happy to answer it if you did. Okay. So all right. So back to this. So everything's a double, and you can actually tell that everything's a double. Oh, I'll show you in a second. Okay. So back to initializing X. So easiest way I can think of to initialize x is to do like what you're seeing in line 3. So let's run that. So first of all, let's look over here in my workspace. What is T? T is in a matrix with one row, 100,000 columns, and each element is, it's a double. Look at that, right? As advertised. Now look at my cheapo way of initializing x. What did I do there? Right, what I wanted was an array x that had the same dimensions at t that was all zeros. So look what I did. I took t, which had one row and 100,000 columns, and I multiplied it by 0. So what that left me with was an array that's also one row, 100,000 columns, but all the entries are 0, because they all got multiplied by 0. And that's it. That's like the cheapo way of initializing x so that you get all zeros. Okay, now I need to enter into my loop. So let's see, what's omega for this problem? Omega was 1. Wasn't that right? Because the period was 2 pi, right? So omega is always 2 times pi over t. We can write it like that. Or should we write it like, I'm trying to think how we can do this in a more generic fashion. Let's say omega 1. I'm just talking about like the actual frequency of the triangle wave. Okay. So now we need to visit a whole bunch of harmonics. So in order to do that, we need a loop, because we're going to do the same thing over and over again, right? So for n equals 1, 2, I don't know, how many harmonics should we do? Well, okay. Well, here's what we learned. Okay, so a couple thoughts about so this is a great question. Like, how many iterations do we need? So the short answer is, obviously, the more iterations you do, the longer it's going to take. And MATLAB is very good, but there's one thing it's very slow at, which is loops. So if you make it do 10,000 loops, like if you have it do a matrix multiplication with 1,000,000 numbers, it'll do it like that. It's optimized for matrix calculations. When you do a loop, MATLAB grinds to a halt. That's just how it's designed. It's fast in some sense and not in the other. So you will actually pay a very real price. I mean, maybe it'll take like 2-3 seconds to do 10,000. So it may not be that big a deal. But more importantly, do you remember we learned that it's like the first few harmonics that give the signal most of its shape, right? And then after that, it's sort of a diminishing returns. So I would expect like maybe by the time you get to maybe 20 harmonics, your signal would be really like have most of its shape. And then after 20, you know, you're going to be like adjusting a pixel here and a pixel there. And so you'll be doing a lot of extra work to give you not that much better extra performance. So that's why I'm like a little hesitant to go all the way out to 10,000. Why don't we start with like 25 and then we can maybe increase it and see what that gets us. Okay, so is everybody familiar with the way we structure loops in MATLAB? Okay, so in case you're not, let's just reiterate. So the words that are in blue, those are MATLAB. I mean, MATLAB turned it blue. I didn't make them blue. But those are kind of the special keywords. So for, so that means that it's everything that between the for and the end is going to happen once for every time in this list. So basically, first n is going to equal 1, and then it's going to iterate through the list. Then n is going to equal 2. It'll iterate through the list, and it'll keep doing my list over and over again until n equals 25. And I can do whatever I want here. Yes?
What if we wanted to initialize like a variable on the top and have it go that many times? Let's say...
Oh, right. Like, so for example, let's say n vector equals 1 to 25. Oops. You want to do like this?
Or you can just make n vector equals 0 and then do n equals the new vector. So
you would still do 1.
I'm not sure I understand the questions. Go ahead.
For loop in Java.
Oh, yeah?
So it's like for x is, or I is less than x, and then you would initialize x at the top as being 35.
Oh, I see.
So
yeah, you could do that.
n vector context.
Yeah, I mean,
I think might answer it, but I've never seen that before.
okay, I mean, you could say this for var equals 25, for n equals 1 to var. You can do that.
Okay.
I mean, that's what you're saying. So in like C in MATLAB, you basically say iterate this loop as long as I is less than some number, let's say. Okay, so there's a true condition that has to be met in order for the loop to keep iterating. In MATLAB, it's different. In MATLAB, you're basically giving it a list of numbers, and it will repeat the loop once for every time that's in that list of numbers. So if I just go back to the way it was, because I think it's a little simpler. So if I say 1 to 25, that means 1:25 literally in MATLAB means 1, 2, 3, 4, 5, all the way up to 25. It'll iterate that loop 25 times. And you can put whatever you want in that list. You can say, for example, if I do like this, that means 1. The :2 means add 2 every time. So you'll get 1, 3, 5, 7, 9. You can put whatever you want in that list. I could just put in a list of numbers, right? Give me the 1st, the 20th, and the 100th harmonic. And it'll iterate it 3 times on those values. You can basically just give it a list of numbers, and it'll iterate through those numbers. Okay, so now let's get to the cosine. So first we need to know our frequency. So our frequency is going to be the nth harmonic, right? So the nth harmonic should be n times W1. So W1 is always going to be the root frequency, in this case 1 radians per second. And now I'm just going to multiply it by n, right? So it'll be 2, 3, 4, and so on. Okay, next I need A, or A sub n rather. So A sub n is going to be, let's see, it was, what's the easiest way to do this? 1 over pi times n times e to the minus j half plus n over 3 positive j. Does MATLAB know what j is? Yes. Yeah, if you don't, you're welcome to use j as a variable, but as long as you haven't used j as a variable, it will assume that j equals negative, that j equals I, or you could just put I if you want to, like that's fine too. Okay. Okay, so let's see, what's next?
How about the pi? Outside the parentheses.
Right there. Have I typed it in right? I think so. Okay. So now I need to create my cosine. So let's see, cosine. So I need. So first of all, what's the amplitude of my cosine? It should be twice the magnitude of A. So 2 times the magnitude of A sub n times cosine. Cosine of what frequency? Not W1, W.
Oh, yeah, W.
Right, because I've scaled it by, okay. So omega t plus, I need a phase angle now. What's my phase angle? Should be angle A sub n. So look what, I mean, this is literally exactly off the equation, right? We said that the amplitude of my cosine is twice the magnitude of A. So ABS is a built-in function that gives me the magnitude of A. There's your cosine. I'm using the right frequency. That's the frequency of the nth harmonic. And then I've got to add a phase angle, which I know is the phase angle of A. And what am I going to do with that cosine? I've got to add it into x. So what I'm going to say is x equals x plus. So take my existing x and add in this new cosine. And when we're done, plot t comma x. Too many arguments. Oh, I got to put a time. Nope. No need to initialize it. There we go. Yes.
Okay. I was working through the recitation problems over the weekend.
And
I don't know if it's a MATLAB problem or a calculation problem, but for the first 2 problems, I would get the shape of my graph right in MATLAB and the period, but my amplitude did not go from 1 to -1. It only went from positive half to minus. And I had that.
did you put the times 2 here?
I did put the times 2 there.
I'd have to look at your code
Okay.
or your hand calculation.
It was just like I said, I wasn't just once. I had it on multiple problems, so I
Right.
the MATLAB problem.
Yes.
Sometimes I know I have to put the dot when I multiply.
Ah, the dot. Do you guys know about the dot for the multiply? I know that this gives people fits in MATLAB. So I didn't have to put any dots here. The only time when you have to put dots is when you multiply two matrices together and you want to do like a pointwise multiplication. So for example, if I have, if I'm in a situation where, let's say I've got some matrix A that's 1, 3, 5, and 7. And I've got some matrix B that's 2, 4, 6, 8. And I want to multiply the corresponding elements of those arrays. Okay, so I want to get, what my goal is would be to have like a matrix C that's equals to 2, 12, 30, and what's 7 times 8? Is that still 56? Okay. So if I just come along and say A times B in MATLAB, MATLAB's going to not be happy. Okay, and the reason is that if you just say A times B, it's going to assume you're going to do a matrix multiplication. So what's the rules for matrix multiplication? Right, your inner dimensions have to work out. So what's the dimensions of A? 1 row, 4 columns. And what's the dimensions of B? 1 row, 4 columns. So do the inner dimensions match? No. So if I multiply them, it's going to complain. If you put a dot, then it knows you're not trying to do a matrix multiplication. Then it just does a dot product, like a pointwise multiplication. Then you're good to go. That's when you use the dot. If you're trying to multiply elements of one array times elements of another array, that's when you use the dot.
If you had transpose B?
Well, it would not give you an error, but it wouldn't give you what you wanted.
Okay.
Right? If I said,
Oh, yeah, that's right.
right, if I said A times B transpose, look at what would happen. Right? So A, in that case, A would be 1 by 4, and B transpose would be 4 by 1. So I could totally do that. But then what would it give you? It would give you 1, 3, 5, 7 times 2, 4, 6, 8. So it would give you 1 times 2 plus 3 times 4 plus plus. So then it would basically just leave you with a 1 by 1, like a 1 number. So it wouldn't give you an error, it just wouldn't give you what you wanted. And that's an important distinction. Okay, so sanity check. I want to know if I got what I expected. Is this right? I don't know. Let's start by putting a grid on there. Watch this. Grid on. That helps. Okay, let's do a few more harmonics just to see what happens. So you wanted to go up to what? 10,000? Let's start by 100. Didn't take too long. 1,000? Okay, not awful. I'm not going to do 10,000. I mean, it's still pretty good, right? I mean, for 1,000, I mean, I can live with that. It's good enough to know that we did it right. It's interesting, though, isn't it? Like, it kind of makes sense that, I mean, let's look at where it fits and where it doesn't fit. So it looks like we got our sawtooth totally perfectly. The only place where it's not like exactly right is right here at these sharp edges. Okay? And it looks like if I wanted to get that sharp edge to fit out a little more, I'd need an even higher frequency. And that's basically what keeps happening. So if you were to look at this signal, where do you think would be a low frequency portion of this signal? Yeah, so you see this part right here, the flat part? That's a relatively low frequency segment of the signal. Like your signal's not really changing that much there, right? Like if I were to, get the slope of that line, it would be relatively low. Which means that if I wanted to fit it with a cosine, I would need a relatively low frequency cosine. And that's good. That's what I've done, right? I've already put the low frequency cosines into my system. So therefore, I should expect a very nice fit at those portions. Now, conversely, where is the high frequency portion of my signal? at the discontinuity, right? In fact, you can't get higher frequency than a discontinuity, right? Like if you think about frequency as a slope, I mean, think about a square wave for a second. If you think about a square wave for a second, like what's the slope right here at this rising edge? Yeah, or like, you know, infinity, right? Rise is 1, run is 0, so 1 over 0 is infinity. Okay, so tell me about what frequency, so if I'm trying to build this out of cosines, what frequency cosine do I need that has a slope of infinity? Really big, right? Like, I can't use this cosine, because there's nowhere on that cosine where there's a slope of infinity, right? I can't use this. I mean, this cosine's a little better, but still, I mean, my slope here is bigger, but it ain't infinity, okay? So if I want to get that slope, I need to keep using higher and higher and higher frequencies. And unfortunately, if I want to get that total discontinuity to be perfect, I need to add infinitely high frequencies, because that's the only way I can get a cosine that's going to be that sharp. So, in our cosine build here, we've included the low frequencies, but did we go all the way out to infinite frequency? No, we went out to 1,000 harmonics and then we got bored. Okay, so does it make sense that the one place where our fit isn't perfect is at the discontinuity? Yeah, because that's the one place where we didn't add enough frequencies. So the reason we're talking about that is to like build some intuition. Like, I want you to look at this signal and think about frequencies. I want you to look at it and think, hey, there's a low frequency portion, which is the slope of the sawtooth, and then there's the high frequency portion, which is the discontinuity. Discontinuities are always high frequencies, right? And therefore, if you try to rebuild this thing out of cosines and you don't include all infinite frequencies, then you should not be surprised to find out that the one place where the fit isn't perfect is right here at the edge. Pretty slick, right? I mean, it all just kind of fits together.
How does it look in the middle, like on a flat slope?
Like right here?
Yeah.
Little chunky. Now that chunkiness I think might be... No, that's actually due to the cosine as well. But again, if you want to get that smoother, you add more frequencies. But still, I mean, relatively speaking on the whole, the fit is worst at the edges and best on the flat. Okay, let's see. Do we get the shift that we wanted? By inspection, we got the amplitude we wanted and the frequency. Okay, what about the shift? What was our shift? Does anyone? I don't even remember. Pi over 3 to the left. Okay. All right, how can I figure out if I got pi over 3 to the left? Let's see. How about I put a data cursor on there? Okay. Can everybody see that? Right. So the x value of my shift is 1.047. Is that a third? So let's see. Pi over 3, 1.047. Look at that right there. I said, hey, what's pi over 3, calculator? It said 1.047, and look, we got it exactly right. So that's a win. Okay, let's talk about some graph aesthetics, because this will feed into Wednesday's. I mean, I think we're going to be able to get like halfway through this, and then we'll start talking about your computer project. So for your computer project, I've asked you to do a couple of tasks, and you should have all read the computer assignment by now. But basically, you're going to be doing some analysis like what we've been doing here on a couple different signals. In the first part, you'll be multiplying two cosines together, I believe, and tell me what the frequency content looks like. And in the second part, you'll be multiplying a square wave with a cosine and giving me that frequency content. So same thing. You're going to do this stuff out by hand, and then you're going to give me some plots. And in all cases, you can verify that you don't ever have to guess that your answer is right, because you can always rebuild your cosine. You can always rebuild your signal using this tool, which I'm going to post online for you, and make sure that you're and see whether or not the signal that you've rebuilt out of cosines is in fact the thing that you were setting out to build. So, I mean, for example, look at this code that I've written here. Is this code only work for my sawtooth? No, right? The only thing to me that's special about this function that's specific to sawtooth is I've got line 5 where I hard-coded in the period of my signal. And I've got line 10 where I've hard-coded in the equation for a sub n. But if I give you some other signal, right, you just type in whatever the period is for that signal. You type in whatever your hand formula is for a sub n. Okay, and then everything else works fine, right? You still iterate through however many harmonics you want to put in the system. It calculates the frequency. It calculates the cosine. None of that changes. So you never have to guess whether or not you did it right. Okay, you can always just use this code and see whether or not the signal that you're building out of cosines is in fact the thing that you were trying to make in the first place. Okay, what if you wanted to plot did John plot the amplitude of a sub n for you? Okay, let's just put that. I'm going to put all this code online, so let's just sort of do this while we're at it. Yeah, let's do the stem plot real quick. Okay, so let's see how we're going to do this. So let's have n equals 1 to 100. Let me just sort of type this out, and then I'll kind of explain what I've done. Figure 2, clear figure, stem. Let me just type this out. It's easier to type and then I'll come back and talk. Stem and okay, so let me tell you what I've done. So now we're just focusing on lines 17 through 24. Oh, you can't see the line numbers. That's tremendous. Okay, so this is what are called the line spectra. So I'm kind of starting over a little bit. What I'm saying is let's start by defining n to be an array of harmonics, starting with the first harmonic going all the way out to the 100th harmonic. So n is now 100 numbers long. And what I'm doing here on line 19 is that's my same formula for a sub n. The only thing that's different from what I'm doing down here than what I was doing above is upstairs, when I was computing a sub n, I was computing like one number for a sub n for every pass through the loop. So on the first pass through the loop, I was computing a sub 1. Second pass through the loop, a sub 2, so on and so forth. What I'm doing here, n has 100 points, a sub n has 100 points. So it's essentially giving me 100 values of a sub n corresponding to the respective values of n. So a sub n will have 100 numbers. The first number will correspond to a sub 1. The second number will correspond to a sub 2, so on and so forth. The only thing I had to do differently was to put dot, instead of dot multiply, it's now dot multiply, and instead of divide, it's now dot divide for the same reasons that we were talking about, because now n has 100 points. So I want to make sure that it's doing just a pointwise divide and a pointwise multiply. Okay, so I create n and a sub n. So now I say, please go to figure 2. So it's created a new figure for me. I have figure 1 where my original plot was. And CLF clears the figure. So go to figure 2, clear it. Now I'm going to execute the subplot command. You see how I got two plots on the same figure? As opposed to like having a separate figure for each plot. So sometimes it's nice to do plots like this because you get like two graphs on the same sheet. It's just easier to compare them. So you do that by executing the subplot command. So what subplot does is it says, take your page, divide it into 2 rows and 1 column. So do you see my 2 rows? So there's one row of figure and another row of figure. and I've only got 1 column's worth of figure. I can do whatever I want. I can make 3 rows and 2 columns or whatever. So I'm saying take my figure, break it into 2 rows and 1 column, and now I'd like my new plot to go in the first slot. That's how that works. So now here comes the stem command. So forget this for a second. I just want to plot the absolute value of a sub n. So that's going to show me the amount that I have of each frequency. All right? And as advertised, you can see that, you know, like the first few harmonics add a whole lot to my, you know, there's a lot of amplitude for those guys. So you should really expect a lot of improvement from the first like 10, 20 harmonics. But sort of once you get out to the 30th harmonic, you know, they're all really small. So like adding the 31st harmonic isn't going to improve your signal that much more over the 30th one. Yeah?
The percentage sign is applied to comment the first.
Oh, the percent sign?
Yeah.
So what the double percent, so percent is a comment. Double percent does this cool trick where it takes your file and it breaks it into what MATLAB calls cells. So it basically says this is a cell and this is a cell. And the nice thing about breaking it into cells is there's a hotkey, but I think it's probably different on most of your computers. On mine, it's Command Enter. But it basically will only run the commands that are in the cell that I'm in. So it just gives me a nice way to only run like a few lines of code without having to run the entire file. Because I don't need to rerun this guy now. He's already done. He takes, you know, it might take a few seconds to run that code. I only want to run this code. So by putting the double percent sign, I can just execute that code and it will only run the current cell that I'm in. It's kind of a nice little feature. Okay, and now I'm going to do another subplot, 2, 1, 2. So 2 rows, 1 column, but now I want you to plot it in the second one. And what do I want to plot? The angle of a sub n. Okay, so sometimes I get close to pi, sometimes I get closer to 0. So the only question left is what did I put on my x-axis? Right, so I didn't put n on the x-axis. This is one place that I'm always critical of the way textbooks do this. So if I just plotted n on the x-axis, that would tell me, that means 1 would refer to the first harmonic, 2 would refer to the second harmonic. But really what I think is more helpful is to put the frequency of the first harmonic and the frequency of the second harmonic. So look what I'm doing here. On the x-axis, I'm taking n, which is 1, 2, 3, 4, 5, all the way up to 100, and I'm multiplying it by omega 1, which is whatever the frequency was for this, whatever the frequency was for this signal. So when we do, when I multiply them, that will give me the frequency of the first harmonic, the frequency of the second harmonic, and so forth. So my x-axis in both cases is frequency in units of radians per second. What if I wanted to do frequency in units of hertz? Divide by 2 pi. Look how easy that would be. Divide by 2 pi. Doop. So the y-axis stayed the same, but now my x-axis, instead of going, is now in hertz. Now, let's talk very briefly. We've got about my watch says 4 minutes. That clock says 2 minutes. This clock says 2 minutes too. Bah humbug. Okay, let's talk very briefly. Title and labels. So, title. Amplitude of sawtooth function. X label, frequency in hertz. Y, I misspelled that. Y label, amplitude, or let's say magnitude. Okay, so we're definitely going to talk more about this on Wednesday, because for me a big thing is making your plots pretty. I want your plots to be pretty. But so MATLAB lets you add, there's this title command. So you say title, open paren, single quote, a bunch of text, single quote, close paren. And what that does is, gives you a title. Ditto for X label, ditto for Y label. Okay. When you do that, no one has any question what's on your axes. You don't have to look at that and be like, dang, is that hertz or is that rads per second or what's going on there? No guesswork. Okay. Make it easy for your reader.
You would do that before subplot, or you not split up.
If I did the
If you did the title before your subplot, which was divided up.
No, you want to do it always after a plot's on the screen, because if you just did a title and then a plot, it would probably just obliterate the title. Yeah, so afterwards. Okay, now everything's like nice and readable. Okay, I have no question what's going on. So, I realize we went through a bunch of stuff and that we went through it fairly quickly. I'm going to put this code online, like right now, literally right now. What I need you to do is go home, download this code, and stare at it till it makes sense. Okay, if you've got another function, like if you did the square wave function from recitation this week, plug the square wave function in for a sub n and see if you can rebuild the square wave function. Okay. Let's work on this, because when we come back on Wednesday, I'm going to sort of assume this makes sense, and we can, we're going to sort of prep. We talk about how to make the plots even more readable. Okay. I'll see you on Wednesday.